everyone, welcome to the course on medical biomaterials. We will continue on the topic of biodegradation and bioresorption. As I mentioned, biodegradation happens when a polymeric material degrades into macromolecules, but the macromolecules can migrate or they can remain in the body. So, that is called biodegradation. So, a large molecular weight material degrades into smaller molecular weight material. So, here we do not need to have the complete excretion of the macromolecule, whereas in bioresorption it is completely degraded and it is eliminated from the body, okay, into low molecular weight molecules. So, example of biodegradation could be ultra high molecular weight polyethylene, where we are talking molecular weight of 90,000 or even 100,000 Dalton. So, it may degrade into smaller molecular weight material and the material may stay inside, whereas in the bioresorption if we take polylactic acid, it gets degraded into say small molecular weight, even lactic acids is formed which is completely eliminated from the body. So, that is called bioresorption. Okay. Sometimes we even call metals as bioresorbable. Corrosion or attrition of metal joints, metal implants, then we get the attreated material which may be removed from the body, excreted from the body. So, this could be much longer time, whereas if we take polylactic acid, it may be happening much faster when compared to. So, these are two important properties, the biodegradation and bioresorption, and nowadays there is a lot of interest in cardiovascular stents. Can we have a bioresorbed cardiovascular stents? Currently they use titanium based alloys and they remain inside the body forever. So, can I have a bioresorbable stent? After a few months it starts completely disappearing. Okay. Can I have bioresorbed or biodegraded orthopedic implants? Okay. So, currently they use stainless steel or nickel titanium type of alloys which remains inside the body and which remains with the bone. Can we have a biodegradable or bioresorbable implant which will completely disappear once the bone has really regained its strength? What about bioresorbed or biodegradable drug delivery system? So, a polymer encapsulated drug is introduced into the body, the polymer gets degraded and the drug gets released. So, in all these situations it is very important to have this particular property. Okay. So, generally there are certain bonds or bond systems which help in the degradation or resorption. So, you need to know those, so that when you are designing polymeric blends, we can think of having that sort of material. For example, if you take say ester bond, okay, C double bond O, this is called an ester bond, or if you take an amide bond, C double bond O NH, or if you take a thioester bond, C double bond O S. So, they are easily degraded either through hydrolysis or enzymatic hydrolysis or acid catalyzed hydrolysis. So, these are very facile system. That is one thing. Okay. Another system where we have carbonates. So, we have carbonates means C double bond O and we have ether linkages on both sides, or urethanes, we have a C double bond O, one side is O, another side is NH, or urea, we have C double bond O, N nitrogen on both sides. So, these are also degradable. Let us look at another system, imide. Okay. So, we have a nitrogen, both sides ketonic, or we have oxygen, both sides ketonic. So, this is also very facile, they can easily degrade through hydrolysis. Okay. So, if you can introduce these type of bond systems in your polymer, you can expect them to degrade or resorb. Okay. So, many polymeric systems degrade, natural polymer or synthetic polymers. Natural polymers like fibrin, collagen, chitosan, gelatin, hyaluronic systems or glucon, cyclodextrins, they all are natural which can degrade. Synthetic like polylactic acid, polyglycolic acid, combination of polylactic glycolic acid, polycaprolactone, polyorthoese esters, polydioxanone, anhydrides, trimethylene carbonate, polyphosphazenes. So, all these or polymers which can also degrade. So, I can have a blend made up of a degradable polymer and undegradable polymer. So, degradable polymer can have the drug which can get slowly released. So, I can think of about different types of strategies by incorporating this biodegradable or bioresorbable material into the design of a biomaterial. Okay. So, I also mentioned surface erosion, that means material gets eroded slowly on the surface, or bulk degradation. So, in the bulk degradation maybe water ingresses very fast and then the degradation happens. It could be acid catalyzed, hydrolysis or autocatalytic type, whereas in the surface erosion the mass loss is much faster than the ingress of water into the bulk. Both types of systems have their advantage and disadvantages. Surface erosion, the material will become thinner and thinner. Bulk degradation, material can one day completely disappear, that is the bulk degradation. So, surface erosion, polyorthoesters and polyanhydrides. Bulk degradation, you have polylactic acid, polyglycolic, PLGA, PCl and so on. And also we have certain minimum thickness. If you have the thickness much less than that, then you can expect bulk degradation. If you have very thick material, chances are you can have a surface erosion. So, we can think about both these type of mechanistic approaches. Then we also have oxidative degradation. In many cases we talked about hydrolysis characterized by catalyst like acid or base or enzyme. We can also have oxidative degradation, where oxidation of the polymer occurs by a homolytic, okay, or it could be heterolytic. So, in a homolytic, so we form radicals, free radicals. So, we can have a free radical formed here. Okay. This can happen when a carbon substituted by an aliphatic chain, or a carbon substituted by aromatic, or carbon substituted by allylic group, that is C double bond C group, or aliphatic like this, or aromatic. Okay. Or we can have situations like etheric or alcohol or aldehyde or phenol. So, all these places there could be formation of free radicals, okay, because of the oxidation, or heterolytic, where one of both the atoms keep the pair of electrons of the chemical bond. So, we can have two free radicals formed, especially in the case of amine. So, these are oxidative. Okay. So, most suitable sites for oxidative are carbon substituted by aliphatic chain, carbon substituted by aromatic, or by allylic group, ethers, phenols, alcohols, aldehydes, amines. So, all these are locations for oxidative degradation. So, activated phagocytes, that means macrophages, neutrophils, release reactive oxygen species. Okay, these activated phagocytes inside the human body, and reactive nitrogen species near the implant, okay, because they start attacking the implant, because the implant is seen as a foreign body. So, they are phagocytes. So, they release reactive oxygen species and reactive nitrogen species. So, first day of implantation, almost 24 hours, 36 hours, neutrophils are released. Okay, and after a longer time macrophages are released actually. So, the first day of implantation neutrophils are released, so they release ROS and reactive nitrogen species. Now, later on the activated macrophages, they are the second line of immune defense, which happens after 2-3 days in case there is an infection. So, as soon as an implant is placed inside the body, these neutrophils release ROS and RNS, so they can start oxidizing your implant. Okay. Then after some time you have activated macrophages, they also they are the immune defense system, they also start releasing these reactive oxygen, reactive nitrogen species. Okay. So, neutrophils and activated macrophages can metabolize oxygen to generate the superoxide anion via the NADPH oxidase, which is transformed into the hydroxyl radical and initiate the oxidation of the polymer surface. Okay. So, both these initial stages we have neutrophils released, later stages macrophages, activated macrophages are released. So, they metabolize the oxygen to generate the superoxide anion through the NADPH oxidase, okay, which gets transformed to OH dot, which can oxidize your polymer. Okay. This is how oxidation takes place. Okay. So, many properties of the polymer which help in degradation, like the structure, composition, distribution of repeat units in multimers, the molecular weight, it may be more easy to degrade smaller molecular weight compared to larger molecular weight. Polydispersity, if you have a very polydispersed material, there will be a lot of smaller molecular weight material which may get dispersed. Presence of low molecular weight compounds, monomers, oligomers, solvents, plasticizers, they may get degraded faster because plasticizers are very low molecular weight. Presence of ionic groups, when you have ionic group you are going to have minus and plus charge on the surface which may help in some of the acid catalyzed or base catalyzed reaction. Presence of defects in the chain, presence of unexpected units, configurational structure, okay, morphology like crystallinity, presence of microstructure, orientation, residual stress, if it is amorphous material are easy to get oxidized or hydrolyzed, whereas crystalline structures are more difficult. Processing methods and conditions, how you have processed it, how did you sterilize the material, how did you anneal the material, storage history, how long you store it, under what conditions, site of implant, where you are implanting the material, because if you want macrophages and neutrophils to be present, so you may have to have a blood region. Okay, if you are talking about hydrolysis through esterase or lipase or that sort of enzyme, so site of implantation plays a very important. Absorbed compounds, what type of material gets absorbed on top of your implant, what are the physicochemical factors like shape, size, mechanism of hydrolysis, is it enzyme catalyst or is it acid catalyst or base catalyst, those things also. So, a lot of properties affect the degradation of your biomaterial. So, what are the factors that enhance? More hydrophilic backbone will enhance degradation, more hydrophilic end groups also can enhance degradation, more reactive hydrolytic groups, groups which can easily react with water like I mentioned, NH, esters, okay, they are all more reactive hydrolytic groups. Less crystallinity, that means if you have more amorphous material then it can degrade faster when compared to crystalline material. More porosity, you have more pores, water ingress can happen, so the reaction of hydrolysis can take place. Smaller device size, smaller material can degrade faster because they can get attacked from all directions when compared to large material. When you take about ceramics, they are also sensitive to variation in pH. Okay. So, in acidic conditions, okay, tricalcium phosphate, hydroxyapatite, all these are bone implant, even dental implants, they can degrade. So, acidic pH can be really detrimental to ceramic material. Okay. So, you need to think if you are having situations in like where the pH is very low, can I use ceramics or should I go for something else. Okay. There are many tools we can use to monitor and measure degradation. Okay. We can look at morphological changes, that means does the material swell, is there deforming, is there bubbling, material disappear. Can I look the morphological changes using a scanning electron microscope. I can look at the morphological changes using atomic force microscope, or I can look at the surface roughness because of degradation using a profilometer. I can look at the weight loss of the material over a period of time, because if it starts degrading slowly the material weight will decrease. I can look at the thermal changes using something called differential scanning calorimetry or calorimeter, which tells you what is happening to the physico-chemical properties. I can look at molecular weight changes. If the material is degrading from polymer to oligomers, the material must becoming smaller molecular weight. I can use viscosity as a measure, I can use size exclusion chromatography as a measure. Okay. I can use matrix assisted laser desorption ionization spectroscopy. So, I can measure the mass using this mass spectrometry. I can measure the molecular weight using size exclusion chromatography or gel permeation. If there are changes in the surface chemistry, I can use infrared spectroscopy or nuclear magnetic resonance spectroscopy or time of flight, secondary ion mass spectrometry techniques. Okay. So many different tools I can use to check what is happening. Now, we can consider this polymer degradation as it is following a pseudo first order. So, we can say the molecular weight, okay, as a function of time could be molecular weight initial e power minus lambda t. This is a first order kinetics, exponentially decaying, right. So, this lambda is a degradation rate based on weight, average molecular weight for all the hydrolyzable elements. So, if a polymer has hydrolyzable and non-hydrolyzable, we will not consider the non-hydrolyzable portion, only the hydrolyzable portion. Applicable when the polymer matrix in the initial stage has no macroscopic pores, because if it has got pores, we need to consider slightly different model. So, it is a bulk polymer and m naught is the initial molecular weight of the hydrolyzable portion, lambda is the degradation rate constant, t is your time. From this simple equation we can find how the molecular weight average molecular weight goes down with time. If it has got a porosity with the initial porosity, okay, alpha, then we just change this equation to mt is equal to m naught e power minus lambda t plus t add. T add is logarithm of 1 minus alpha divided by lambda. Okay. So, how this equation is got is at initial time it has got a porosity alpha. So, if you go in the negative time, at some point the porosity could be 0, that means you have a solid bulky material. So, this T add is the time taken for it to reach from 0 porosity to porosity of alpha, that is what this is actually. So, if the polymer is a bulky material, okay, there are no pores, we can use this equation for determining the change in the weight average molecular weight as a function of time. If it has got initial porosity, then we can use this equation to calculate the weight change in the weight of average molecular weight as a function of time. Okay. So, if I know the lambda, I can follow the molecular weight and we assume it to be exponential. This is based on this particular reference. Okay. There is something called autocatalysis. Autocatalysis is initially the rate of degradation could be slow. As you keep forming some maybe acidic products or ionic products, these may be catalyzing the reaction further and further. So, the rate of reaction may be picking up very fast. Okay. So, autocatalysis accelerates local hydrolysis, thus affecting the degradation rate of polymer devices. So, the extent of autocatalysis is governed by the diffusion process and also it depends on the device size. Okay. And the critical polymer thickness should be less than 10 to 15 micrometer, at which the theoretical autocatalysis free degradation can be approximately achieved. So, if you have very thin material, okay, less than 10 to 50 micrometer, then we can say autocatalysis may not be happening, but if you have thicker material, we can say autocatalysis can be happening if the degradation products are like acidic, like if you take polylactic acid, when it degrades it gives you lactic acid which is acidic, which may enhance the degradation further and further. So, your rate of degradation picks up very fast. Initially degradation could be slow, then the rate picking up very fast. Okay, that is called autocatalysis. You can have enzymatic degradation, enzyme has to get adsorbed, then degradation can start, like in collagen. Collagen monomers in solution are digested according to Michaelis-Menten kinetics. You remember Michaelis-Menten kinetics for enzyme reaction. So, degradation of fibrillary collagen depends on its age. Freshly reconstituted collagen fibrils behave similar to diluted because cross links can still be hydrolyzed rather easily. So, when it is freshly made, the cross links can be easily hydrolyzed, okay, whereas if it becomes older and older, the cross link becomes very strong, okay, then it is very difficult for you to degrade. Degradation of fibril collagen samples with more stable bonds or a higher degree of cross linking is hyperbolically dependent on enzyme concentration. So, we need to have more and more and more enzyme concentration to degrade very old collagen, or if it is highly cross linked, whereas new collagen, and if it is less easily cross linked, it can be hydrolyzed. Okay. So, here we need enzymatic, whereas in the other one we can have hydrolysis. So, if you are talking about enzymatic degradation, we need to have the enzyme adsorbed and then degradation. So, we can assume Langmuir type of adsorption combined with degradation. Okay. So, where adsorption is faster than degradation. Okay. So, we can consider this type of reaction V naught where V naught is the rate of reaction is equal to K E naught A divided by E naught plus 1 by Kd. 1 by Kd is equal to Km, K is the degradation rate. E naught is equal to the E plus Ea, because enzyme may get adsorbed on the polymer surface, but not all adsorbed enzyme molecules must lead to enzyme substrate complex. That means not all the enzyme that gets adsorbed will take part in the reaction, because there could be some enzyme which may be adsorbed, but it is not going to hydrolyze the surface, okay, because absorption can also occur at sites which cannot be cleaved. So, we may have on the polymer surface some sites which may be cleavable, some sites which are not cleavable, but your enzyme may get adsorbed in so many different places also, okay. So, we need to consider those aspects here. So, we are talking about adsorption and reaction of the polymer, okay. So, we are considering Langmuir adsorption and we are considering a Michaelis-Menten type of reaction, okay. Okay, let us look at a couple of problems, very simple problems, but it gives you an idea about what happens to degradation, because when you do degradation you may increase pore size, when you do degradation the polymer strength also may increase. So, is it advisable? We need to consider, and whether the polymer strength goes down much lower than what is really you would like to have. An implant made up of a polymer with an initial porosity of 5% is undergoing bioresorption, that means it is slowly disappearing, so that its porosity is increasing like this, you know. So, initial porosity is 5%, so the porosity is decreasing as a function of time. So, there is some constant, this is called degradation rate constant. So, this is an exponential, this is a equation obtained like this. So, Kn is the degradation rate constant based on number average molecular weight, this is 0.02 per month, and this has got a unit of per month because you have time here, right. The modulus of the dense polymer without any pores is 3.5 gigapascal, that means without any pores. Calculate the modulus of this material after 5 years, use Voigt model, okay. So, modulus is also very important because the strength, tensile strength will change depending upon the modulus, and as the polymer starts degrading, bioresorption, so the porosity increases, so the modulus will keep decreasing. Now, the Voigt model states modulus of a biomaterial is combination of modulus of air and modulus of polymer. The initial porosity is 5%, so modulus of air into 0.05, so we can neglect this term. So, modulus of polymer A into 1 minus 0.05, okay, because 95% is material, 5% is air, that is initial. So, when I put modulus of polymer here as 3.5 and this is 0.95, I get 3.325 gigapascal. Do you understand? This is the Voigt model. Voigt model assumes it to be addition, linear addition. So, if you have porous material, we can neglect that porosity of that material, we take the remaining porosity and then multiply the modulus of the polymer to get the modulus of the biomaterial. Now, there is a degradation, so phi keeps increasing. What is happening to the modulus after 5 years? Okay. So, porosity when T is 60 months, 5 years, so 5 into 12 is 60. So, we put in these terms 0.05, okay. Then this is 1 minus 0.05 into 1 plus exponent of minus 2 into 0.02 is this term into 60 minus 2 into exponent of minus 0.02 into 60, that gives you 0.5139. So, you see the porosity has increased from 0.05 after 5 years it has become 0.513. So, almost 50% of the material is porous. Now, we need to put it in the Voigt's model, so that 51% will not contribute to the modulus of the biomaterial, the remaining 49% will contribute. So, the modulus of the biomaterial after 60 months, so modulus of air into 0.5139 plus modulus of polymer into 1 minus 0.5139, that gives you 1.7 gigapascal. So, what has happened? The modulus of the biomaterial has gone down in 5 years from 3.3 gigapascal to 1.7, almost half. So, is it desirable? That is what you have to see. So, if you have a material and it is losing its modulus, so its strength is going down, So, we need to see whether it is desirable or not desirable. So, depending upon the type of application, type of situation and so on. Let us look at another problem. Okay. A polymeric biomaterial of circular cross section of modulus 4 gigapascal is under constant force. Okay. So, especially maybe in orthopedic situations, the force acting on it is 100 Newton, its original diameter is 2 mm and it is degraded at the rate of diameter equal to diameter exponent minus k into time. Okay. K is 0.002 per month. So, the diameter is becoming smaller and smaller. So, obviously cross sectional area is becoming smaller and smaller. Okay. So, the force acting on it is 100 Newton. Okay. So, it has got a 4 gigapascal. So, obviously stress is going to change. What will be the increase in stress after 3 and 5 years? Okay. 3 years is 36 months, 5 years is 60 months. So, original diameter is 2 mm. So, diameter changes as a function of e power minus 0.002 into 36. It becomes, so the diameter has become 1.86 mm, whereas if you take 5 years, that is 60 months. So, if you put here, the diameter has become 1.77 mm. So, area is pi d square by 4. So, diameter is this, original area is 3.14 mm square. After 3 years, it has become 2.72 mm square. After 60 months, it has become 2.47 mm square. Stress is Newton per area, right? That is 100 Newton. Okay, the force is constant, whether it is 0 year or 3rd year or 5th year. So, 31.84, okay, force by area, force is 100 by area stress, then force by area 100 by 2.72, force by area 100. So, the stress, as you can see, is increased from 31.84 Newton per millimeter square to 36.7, 15% increase in 3 years, 40.47 Newton per millimeter square, that is 27% increase in 5 years. Okay, so the stress has increased on the biomaterial at constant force in 3 years and 5 years. Almost in 5 years it has gone up by 27%. So, we do not know whether it is desirable or not desirable, will it cause any issues. So, you need to see depending upon the situation where you have. Okay. So, in places where this type of degradation is not desired, as you can see in this particular example, stress has gone up to almost 27%. Okay. So, we need to consider what to do if that is not desirable. Okay. So, in the past 2 classes we talked quite a lot about biodegradation and bioresorption, what type of functional groups enhance, and we looked at autocatalysis, we looked at bulk degradation and surface degradation, we looked at functional groups which lead to this type of biodegradation. Then we looked at very simple problems, but they are very useful for you to understand what can happen to some of the mechanical properties when there is a degradation, both in the case of bulk as well as in the case of surface erosion. Okay. Thank you very much for your time.